So yeah, now we have the whole board here. So let us just continue with our diamond class. We stopped last on Wednesday, we stopped with this figure here, yeah? I told you we have to subdivide kimberlites and lamproids. Kimberlites are always so pure and old, are here tradons, like here the Kimberley block in Australia. And if we have some kimberlites or diamond ore deposits in the mobile belts, then we are talking not longer we are not talking longer about kimberlites, we are talking then about lamproids. So in these lamproids, they occur only in Australia. Yeah? Lamproids are not that rich in diamonds compared to kimberlites because lamproids contain more water. And if they are containing more water, then the oxygen fugacity is higher. You know this by now. And the other thing is, then the kimberlite becomes slower because of the higher viscosity, and therefore diamonds showing a higher rate of resorption. So that I told you also on Wednesday. So and now we are coming to the next thing. How does such a kimberlite pipe look like? So here we have a cross section. We have here and below we have everywhere very small seals, yeah. So and these seals, they are running along faults, and these faults are maybe in diameter about 1 meter. Yeah? They are not bigger like this, yeah. So these are the very narrow pipes. So in the upper part, the kimberlite becomes the more explosive. So and then you are forming such a champagne glass shaping upper part. And there you have then, because it becomes then here more explosive, because you are sucking always more and more water out of your kimberlitic belt to form this serpentine. Therefore, you are enriching it more and more in CO2, and then it becomes then in the upper part more explosive, which you can see in the next illustration actually better. So here we have such a diatreme. Here we have the root zone, yeah, and in this root zone we have here these dikes, diatreme related dikes they have written here. So and they are maybe 1 meter wide, yeah. So, and in the upper part you have then here the diatreme fascias. So and there you have a lot of pyroclastics. Here you have a crater fascias. So, but as I told you last week or on Wednesday, a kimberlite is not like a volcano. So where you are forming really a crater, yeah? Because it is not erupting. I mean, it's a little bit erupting, and therefore you are forming here a very small pyroclastic tooth ring, and here we have inside we have epiclasts. So within this diatreme, they are mining then, yeah? Therefore, you are getting these typical, very steep holes where we can find the kimberlites, or where we can find the diamonds. So that is the way how it looks like. Diatreme-related dikes. Here you have the root zone, and then here it is blowing up, and you are forming then in your diatreme fascias, you have this champagne glass shaped kimberlite. So I have shown you this also before. Here, for example, we have a cross section, and that is from where is this kimberlite? Allendale. So that is in Australia, and that is here from a lamproid. So here that is We have here two pipes. Yeah, I told you, or I showed it to you also in the first session when we were talking about diamonds. There I showed you these pictures from the Chaneng mine, and there they have two pipes, and here in this model they have also two pipes. In Chaneng, for example, they have three pipes. So and here they have then a cross section here in scale 500 meters. So then we have here a fluoropite olivine lamproite that is here in the center. Then we have here some olivine lamproites. Then we have here a olivine brachia. Here in the outermost rim we have a lapilli tooth. So in this lapilli tooth, I told you in ES303 about lapillis. Lapillis, these are very roundly shaped spheres, or I mean they are spheres with a diameter of about 5 millimeter, and they occur always when your melt is coming in contact with water, and that shows then that you have then there, or it was then explosive, yeah, at the end, at the stage close to the Earth's surface. Then you have here a sandy lapilli tooth, and here in the surrounding area you have a Permian sandstone. So, that is how such a crater facies looks like. So when they are becoming here on the surface, they are becoming broadened up. You can see it here. We have here 500 meter, then this is maybe 600 meter. This one is smaller, maybe 250 meters. But if you are going more into depth, then they are becoming smaller and smaller till they are becoming very narrow with a diameter maybe of 1 meter. So these are some pictures from diamonds itself. You know by now they occur in different shapes, that means in different crystallographic systems. And here number 8 is a very nice shaped one, and that is an octaedron, yeah? So, and if you can find, or if they find such an octaedron, then it has actually a higher value. So then number B, that is a stacked layered octaedron, and you can see here the layers, yeah? So, and there are coming from, or these stacked layered octaedrons coming from the Udahaya kimberlite pipe, and this is the one in Russia. Here we have the next stacked layer octaedron, and you can just clearly see, or the steps are clearly seen here. Number D, what is number D then? That is a resort, that is also an octaedron, like you can see here. But this one shows then a higher grade of resorption, yeah? So, and if they are showing a higher grade of resorption, that means that the oxygen fugacity was higher from this kimberlite, which brought this diamond to the surface, compared to this diamond, or compared to this kimberlite, which brought this diamond to the surface. Then number E, that is also a distort, that is a little bit a distort octaedron. You can see it here. Here our faces are more roundish, and here you can see some steps. And number F, that is a cube octahedron. Here you have the cube. And these cube octahedrons are actually more seldom. So I showed you when we started with the class the different shapes what they found in Lenzeng. And here these diamonds, they are coming from the Udachaya kimberlite pipe in Russia. And here we have some others that is also Udachaya. And that is from a Canadian pipe. So that is the shape how diamonds look like, or gem diamonds, just without cutting and polishing. Yeah. So here we have then some other shapes. Here we have also octahedron, but here that is a dodecahedron, also from the Udachaya pipe. Here also a dodecahedron. What is number C? Number C is something that is an octahedron with that is the octahedron from the argil lamproite, that is then from Australia. That is then a very nice one. That is a cube. Yeah, one can see it very easily, but this cube shows then also a small degree of resorption. Resorption you can see always very nicely when just the corners are rounded up. Yeah. So here number E, that is a flattened dodecahedron. It shows also a small degree of resorption here. So a number F, that is an irregular form. Yeah. So in these irregular forms, these are actually dominated. Yeah. So and if you have these irregular forms, then I mean they become also cutted and polished. Yeah. But then you have more trash. So if you have a very nicely shaped cube like this one, or a very nicely shaped octahedron as the one on the last page, there you have the less trash. Yeah? You can when they are cutting and polishing them, then they have not to remove that much. So because it is originally in a good shape. Yeah? So they have just to make it nicely. So, but whereas if you are looking for such an irregular shape like this one, then you have to remove a lot of parts to get it in an originally nicely shaped diamond. So, and therefore they are using the large material. Yeah? Or this one here, also a very nice cube, yeah, with very low degree of resorption. Whereas number B, that is then more an irregular shape. Here we have some octahedral aggregates, yeah, that is here one and here one and here one. They just grew together. So and now there you have then also be carefully while you are cutting them, then you that you get less, that you have to less as possible to remove. Yeah, that you get from this one. You can from this one when you are cutting it here, then you get still a very nice shaped diamond. But these parts here and these parts here, they are just ending up as sandpapers. So here the same, you have here a very nicely shaped one, and here another one grew on it. So that means you have to cut it here, you have to cut it here, and this one is trash. The next one here, number E, I mean that this is one which shows a higher degree of resorption. And here we have then also octaedral aggregates which showing these steps. Yeah. So if we have 2 or 3 or diamonds together, like twins, then we are talking about aggregates. Yeah. Whereas here we have just very nicely shaped single diamonds. So now I showed you some pictures how they look like. Yeah, it's all uploaded on Moodle, and then you can observe or watch them by yourself and reading the text release again. So because if you're opening on your own PC or Mac or whatever you have, then the pictures are coming better out. Yeah. So, but now we have this. We have diamonds, so we have seen diamonds which show a lower degree of resorption, and diamonds which shows a higher degree of resorption. So and this I told you that it depends on the oxygen fugacity. If the oxygen fugacity is high, then the diamond shows a higher degree of resorption. If the oxygen degree is low, the oxygen fugacity is lower, then we have a lower degree of resorption. Yeah, and I told you also you can estimate this by checking the ilmenite. Yeah. So and now I have some diagrams. Now I have some diagrams. Yes, these are very nice and confusing diagrams. We have here the oxygen fugacity, and they are using here again the log. So you know this by now. Also from other calculation, we are using very often the logarithm, because then the curves getting more smoothly and it is better for the overview. So and here we have for oxygen fugacity ranging between -10 and -5, and here we have 0, and here we have -10, and then we have here the temperature. So and if we have, if we are checking here for this field, then we have here 600, 800,000 degree, we have here 900 degree, and here in this shaded field we have then a proper oxygen fugacity that diamonds can be, or that diamonds can survive till they are coming up to the Earth's surface. So here we have now a bigger scatter. We have here oxygen fugacity ranging between 0 and -10, and here we are ranging temperatures, having temperatures between 1200 degrees Celsius and 1700 degrees Celsius, and then this is our field, in this shaded field where diamonds can survive. So, but now we need here the single parameters. Yes, these are at different pressures. That one was done with an XCO2 of 0.1. So this diagram was also done with an XCO2 of 0.1. So, but here the calculations have been done using a pressure of 4 gigapascal. So 4 gigapascal, this is 40 kilobars. And 40 kilobars, when we are talking about 40 kilobars, then we are sitting in the depth, let us say, of 130 kilometers, yeah? So 130 kilometers, that is then when we are out of the diamond stability field, yeah? Because the diamond window is between 175 and 250 kilometers, something like this. So there, our kimberlite is already on the way up to the surface. Therefore, we have here the lower temperatures, yeah? So, because I mean, if this kimberlite is shooting up to the Earth's surface, then in a depth, let us say, of about 200 kilometers, we can expect temperatures there of about 1,200 to 1,300 degrees Celsius. I will show you this in next week in the class, because there I will show you some PowerPoints from my own research. Yeah? So, and I have calculated all this stuff by myself as well. So there our kimberlite is then already on the way up, 800 to 900 degrees Celsius. We are sitting then in a depth, let us say, of about 130 kilometers. So, but when we are looking at this one, here the thing was done using a pressure of 6 gigapascal. 6 gigapascal, we are sitting then in a depth, let us say, of 190 kilometers or 195 kilometers. Yeah? You just multiply the pressure by 3.3, then you are getting roughly the depth. Yeah? So that means here, by using the conditions from this diagram, we are sitting then in a depth of about 190 kilometers. That is in the diamond window. There we have just the beginning from the lift up. Yeah? So when the kimberlite is just shooting through a diamond bearing field and samples them and bringing them up to the surface. So, and here we are having a temperature ranging between 1,200 and 1,700 degrees Celsius. Probably we will not have 1,700 degrees Celsius in a depth of about 190 kilometers. We have there a temperature, let us say, I told you just before, of about 1,300 to 1,400 degrees Celsius. We are sitting somewhere there, yeah? So in there we have quite a huge stability field, yeah? So in there we are sitting in the diamond window, and all our diamonds in this step, at this temperature and oxygen fugacity, they show no resorption. They are perfect, there's no degree of resorption, yeah? So that happens all through the lift up. So and then our kimberlite rises up and the oxygen fugacity change, yeah? The pressure condition changing, the temperature conditions are changing, and if we are then during the lift up out of the stability field from the diamonds, then they are just resorbing. And that happens within a couple of minutes, yeah? So, and this we know from experiments. There are some Russian ladies, they are sitting somewhere in Canada, yeah? They are doing all these experiments. So they are using the diamonds, and then they are putting them in a synthetic kimberlitic melt, yeah? You can produce such a melt in the lab, yeah? So, and then they are putting them in, then they are holding the melt of a certain temperature. They can also make pressure experiments. There they have huge presses, yeah. So and then with these huge presses, you can go up to 100. No, not 100, but maybe you can go up to 10 gigapascal, which are 100 kilobars. Yeah, you can produce then a pressure which occurs in the Earth's mantle of in a depth, let us say, of 300 kilometers, 400 kilometers. These are huge, huge presses, which are very expensive, and then you can do these experiments. And then they discovered if the kimberlite is longer than 20 minutes on its way from the diamond window in a depth of 200 kilometers to the Earth's surface, and if the process takes longer than 20 minutes, then they are gone. So, and if they are on the way, let us say with the speed of a jumbo jet, I will show you then some diagrams. Yeah, that is 800 kilometers per hour. 800 kilometers per hour, it's about 333 meters per second, and that is railway speed, yeah? That is Mach 1. So, and then they are stopping very close to the Earth's surface, very fast, and due to the fact that they are so fast on its way, they are not like volcanic eruptions. Yeah? In ES303, I told you that you have assimilation and contamination and fractionation and everything. And then you have an ascending melt, yeah? And some normal melt from a volcano is on its way, let us say, with a speed ranging between 6 meters per second and 36 meters per second. So, and here we are talking about 300 meters per second. So, what is this now? That is just a distribution or the kimberlite pipe in certain depth. Yes, but it's not useful for us. This one we also don't need. This one as well. This one as well. This one as well. This one as well. So yeah, here that is again such a diagram that was created at a pressure of 8 gigapascal. There we are sitting then in a depth ranging between 240 and 260 kilometers, and there you have your stability field at higher temperatures ranging between 1600 and 1800 degrees Celsius. So, and of course, if you have then the lift up, then our temperature will run or becomes then lower and lower and lower, and therefore our oxygen fugacity will change, and that is then always the thing which has to be kept in balance when our diamonds are not resorbed. So it is then actually, it is a dynamic process. So here another table, also depending here on the pressure. We have here 4 GPa, 6, 8, 7 and 6 or whatever it is. So and there we have different mineral assemblages which we can find in a certain depth in your kimberlite. So because the kimberlite itself is also always changing their mineralogy on the way up to the Earth's surface. So, and due to the fact that you are always creating then some other minerals, then the oxygen fugacity will always change. That is the thing. So, because at temperatures higher than, let us say, 600 degrees Celsius, you will not have or you will not form any serpentine. You know this also from ES303. And the serpentine is a very water-rich mineral, and that will then suck out always the water from your kimberlitic melt. and therefore your oxygen fugacity will always change. So then that looks like something like this. I mean, you know how to calculate it by the X ratios. So and if we have X H2O, that you are calculating H2O divided by H2O plus CO2. So and if you are always removing more and more water from your melt, yeah, then relatively to this, the CO2 concentration will increase, yeah? That's the same as with the XMG and whatever we have calculated by now. So and therefore with skipper like X like a catalytic converter. So because you are always changing during the rise up the concentration of your volatiles or the ratios of your volatiles. So when you are starting to form in your kimberlite, the calcite for example, then you are removing CO2. Yeah? So therefore the ratio change again. So but then you have in your kimberlite, as I told you, you have also minerals like phlogopite, there, that is the biotite, you know this by now. And amphiboles, they are also hydrous minerals, and when they become formed, then you are also changing the XH2O, and always when you are changing your XH2O and you are changing it for the whole way from the rise up from the Earth's mantle to the Earth's surface. So and here you have then always some other minerals in your kimberlitic belt which becomes formed. So when they become formed then, always in a certain depth, at certain temperatures, and to a certain volumetric concentration. Yeah? Did you get this? So here we have a more useful diagram. Here we have again the temperature between 550 and 1500 degrees Celsius. Then we have here the depth from Earth's surface to 200 or a little bit more than 200 kilometers. And here we have the pressure in kilobars. So and then you have here different minerals inside which occur together at certain temperatures and certain pressures. So and here for example you have phlogopite, you have dolomite, and V that is volatiles. Yeah? So if you are forming here the phlogopite, then you are removing water from your melt. If you are forming dolomite, then you are removing CO2 from your melt. But you have still vapor. Yeah? So here you have the different geotherms from the shield. Here you have the shield geotherm. And along the geotherms, you can expect at certain temperatures. And you can calculate which minerals they are stable. So here we have, for example, H2O. We have not longer here volatiles, which is a mixture between H2O and CO2. Here we have water, and if we are cooling down from here to here, then we are forming then the serpentine, for example, yeah, or a lot of serpentine, which makes then the kimberlite more and more slow. So in this, what you can see here, you have a peridotite at this field with no volatiles. Yeah? So and if you have there no volatiles, that means there your diamond does not show any degree of resorption. Yeah? So, but you need these volatiles that you can then form the kimberlitic melt, yeah? Because otherwise, without volatiles, you cannot form any melt. You know this by now as well. So it is a very tricky thing. First, you need an area where you can form them that is just under certain pressure and temperatures. So then you have to bring them up. Therefore, you need a kimberlite to bring them up to the Earth's surface. So, but you need a kimberlite which is not destroying them, yeah? Because otherwise it's again useless. Yeah? So here, for example, that is now also a curve, or curves which you have seen now a lot. You have seen them in ES203, you have seen them in ES301, and in ES303. So, and that is always the game. Here we have the liquidus, yeah, and here we have the solidus. So, and within the liquidus and the solidus, that is the dangerous field for our diamonds, yeah. I mean, if the whole kimberlite is then solid, then it stops and all the mineral reactions are done. Yeah? So, and if we are having here the liquidus, here we have then our kimberlitic melt. It runs from here to the Earth's surface, and then here the melt becomes then more and more solid. And if we have then a solid situation, then our resorption will also stop, yeah? Because mineral reactions stop it then as well, yeah? Because that is then our freezing stage. So yeah, that is then this picture again here. Here, just to repeat the whole thing, here we have our the mobile belt. That means we are forming here lumbrites. Here we have our different diamonds. We have eclogitic diamonds. These are the E-types, which are associated with eclogites as xenolites. Then we have the P-types of diamonds. You know this by now as well. They are associated with the peridotites. Yeah. So and then we have here kimberlites. And the kimberlite has to sample the diamonds at first. If the kimberlite rises up from here, then they are not running inside the diamond window, and then they cannot sample diamonds. So, and then they have to bring them up to the Earth's surface at a certain volatile ratio. That resorption cannot take place, or only in minor ratios. That is actually the whole thing, what you have to know, or the important things what you have to know about the diamonds, yeah? So, and I have written up a summary for you as for the other chapters as well, and we will go then on Wednesday through this summary. And then we are done. Yeah, I will show you then also these things what I, for my own research, I will show you today also one PowerPoint from my own research. So another thing, there are the fake diamonds around, yeah? So in these fake diamonds, they actually don't look like diamonds. I mean, from the shape, they are looking exactly the same because they are cutting this and polishing this. But if you are putting a diamond against the light, so and then you can see a huge color spectra. It looks like just beautiful. So, and the fake diamonds, they do not have this. So now something to the fake diamonds, they can be made out of glass, yeah, just from the window, yeah. So then you can use zircons, you can use some strontium titanites, and you can use some, it is not good to read, aluminium-rich garnets, gallium-rich garnets. So, and they show then other optical and physical conditions. So I mean, you can, the most easiest thing is that it's the hardness. I told you the diamond is the most hardest mineral, and you can scratch everything else with it. So, but if you have glass, then the glass has then a hardness of about 7. If you have garnet, then they have a hardness of about 6.5. That is actually the easiest thing to distinguish if they are natural or real diamonds, or if it is a fake. Here they have even used the rutile, yeah. And some other features are here shown in this table. Another thing is, what a lot of people working on, or what a lot of few people are working on this, how long does the diamond stay in the Earth's mantle? Are they formed during Archean time, or are they formed later? So, and therefore they are measuring the nitrogen concentration in single diamond crystals, and then they can make estimations how long this diamond has been resided in the Earth's mantle. So here we have the total nitrogen in ppm, and here we have the lab variation in nitrogen. So, and then they have plotted this or made these curves. So if we are looking at this curve, then they have resided 600 million years in the Earth's mantle. If we are looking at this curve, then they have resided 400 million years in the Earth's mantle. And if we are looking at this curve, then they have only resided 10 million years of the mantle. So for you as an ES301 student, you should just remember or know that one can use the nitrogen concentration in single diamonds and calculate then the time, how long they have been or resided in the Earth's mantle. So that has no influence of the value of the diamond. That is just for academic purpose, to understand or to know more about the Earth's history. This we don't need. This as well. So that was now the PowerPoint. So then here some figures. I have actually 13 figures, yes, that we can talk about till 6:30. So that is one of my studies. I will show you also next week some other PowerPoints from my own studies, because there I have the color figures, and they are showing then actually the same as I told you from theoretical things in class. So here we have then this first slide here, or this first picture that shows just the cross section through the Earth's mantle. So here we have the continental crust. So and below here we have the Earth's mantle. Different isotherms here, 800 degrees Celsius, 1000 degrees Celsius, 1200 degrees Celsius, 1400 degrees Celsius. So, and then the different units here, for example, we have dunites, yeah? Dunites, Harzburgites, and Lersonites. So, and that is this is actually the subcontinental mantle. You know this by now, that it's just below the crust, yeah? So then I have here made these ones, the dark green stuff with the red bubbles or the red dots, and these are then the eclogites, yeah? So that is actually the situation for a cross section, how it looks like beneath the crust in Botswana and South Africa. Here actually Botswana, because that is one of my Botswana studies. So and here we have then deformed lersonites, yeah? So they become deformed because of the upwelling of the convective mantle, that is one thing. Or they can become deformed because of some tectonic forcements. So and here we have the convective upper mantle, ranging here in a depth between 200 kilometers, which is quite deep. So and that is our heat source, yeah? So here the convective mantle in Fiji is much more close to the surface. So that's the reason why you can find here everywhere these hotspots, yeah? So if the convective mantle here is sitting in a depth of 200 kilometers, that means you will not find any hotspot there in South Africa. So and here there is this convective mantle. And the next slide which I made here, that is here just the distribution of the thickness of the crust, and that you can do by using geophysical methods. So the geophysics is also a small chapter in ES301, and we will be talking by the end of the semester about geophysical methods, also from my own studies. So and then I have used different colors here. So and here we have a crustal thickness ranging between 56 kilometers and 28. That is just this thickness here. And the samples from which I'm now talking about, they are coming from the Chaneng mine, and the Chaneng mine is here. So that is just in the west of Gaborone. It's maybe 150 kilometers. I was there a lot of times. I will also show you or bring you a kimberlite from the Chaneng mine. I have some of them in my office. I was there very often, and it is the biggest diamond mine in the world. I told you that at the beginning of the class they have a very high degree on gem diamonds. So, and we are expecting here a crustal thickness of ranging between 47 and 50 kilometers, that is here. So then I have here a red stroke line, and here is a red stroke line. So, and that marks then just a boundary here of a former subduction zone, yeah? So you have here a subduction zone, but it is a very old subduction zone. So, and that is just a figure which I have modified from these figures. What I showed you also before. So, because nobody knows it really how it looks like in the Earth's mantle, it's just some ideas. So we have at first, we have the formation of a depleted continental lithosphere, and that is something how it looks like 2.9 billion years ago. You can preserve here the diamonds in the diamond stability field, which is maybe known here. So, and here we have Gaborone, that is the eastern shield, and that is the western shield. And here this stroke line that marks up the suture. So that is this reddish line from figure 1, the reddish dotted line from figure 1, which I showed you just before. So then here again, we are using this model, we have thermal erosion and the preservation of diamond above the mechanical boundary layer, and the mechanical boundary layer, that is this one. Here we have thermal erosion, and thermal erosion that is actually ventral metasomatism, and that is caused by the convective mantle. So, and it is a depleted mantle, and the depleted mantle, that means it is very close to the chemical composition of more or the chemical composition of the chondrite. Yeah, it is an ES301. So, and this is an ES303. Yes, you have the depleted stuff and you have the enriched stuff. So, in the enriched stuff, you are forming them later. So, and here we have diamonds of different age. You have younger diamonds, 233 to 440 million years. So, and you have older diamonds of an age of 1,540 million years. So, and the kimberlite in Chaneng erupted during Jurassic time at about, I think, 230 million years, what I have written here, yeah. The kimberlite eruption was dated in Chaneng between 206 and 245 million years. So then these diamonds here are formed close or formed when the kimberlite was formed and erupted. Yeah? So because from my study and also study from other people, diamonds must not necessarily form in the diamond window. I mean the big ones. The big ones, they are formed in the diamond window because there you need time to form them. Yeah? I mean, you know this by now, if you have a big mineral, then it takes longer or much more time to form them as the very small guys. Yeah? So the micro diamonds can be formed out of the diamond windows by during the uplift from mineral reactions, and these are mineral reactions that is not a transition, or it's not longer a polymorphic transition from graphite directly into diamond like for the big one. They are formed by polymorphic reactions. But that is now not important for you. Here is important, you have different diamonds formed while the kimberlite was formed and lifted up, and then you have some other guys, and they are formed in the Earth's mantle long time ago before, and they are then chemically different from those formed while the kimberlite erupted. So, That means below our feet, not here below our feet, because here we do not have the necessary thickness of the crust, yeah? But maybe when we are waiting another 200 or 300 million years, then we have here also the necessary thickness. So, but that's for now the thing what I like to tell you. It could be in a lot of parts in the world that islands are just sitting in somewhere in the Earth's mantle, yeah? They are just sitting there, yeah? So nothing happens to them. No lady can hang them around the neck because they are still located here in the Earth's mantle. So then, also what I told you now a lot of times, you need then a kimberlite or a lamproite to bring them up to the Earth's surface. So and therefore we have to create a kimberlitic melt, and therefore we need a source. So and here I have again this megalite, yeah, and this megalite is just a remnant of old subducted oceanic crust. So that you know the oceanic crust is covered at the top with sediments and so on, yeah, and they are very wet. So they are very wet, you can easily create a melt from these sediments. So and then these sediments, they are very rich in calcium. They have also a lot of potassium oxide, that is just from weathering from the continental crust. Yeah, you know this by now, weathering continental crust. You are transporting your sediments on the ocean floor or in the trench, let us say more to the trench. Then the whole thing becomes subducted, and now these sediments, I mean, they are high-grade metamorphic rocks. These are not longer sediments. You are making at first from your sediments, they are undergoing metamorphism, yeah? We have done this last year in ES301, when we are talking about metaphylites, yeah? So, but then these metaphylites becoming dehydrated, and then you have an enriched mantle there, yeah? So, and then this mantle is enriched, for example, in potassium group elements. You know this by now as well, potassium group elements, strontium, barium, rubidium, blah, blah, blah. So, and these potassium-rich elements or potassium group elements you can then find in the kimberlite, yeah? So, and then the kimberlite is just sitting somewhere there. So, you are forming their liquid pools. So, or let us better say, we are thinking that we are forming their liquid pool. It could be in 50 years a totally different opinion, yeah? Because that's always the thing. To do studies in the Earth's mantle is actually much more complicated as to work on rocks from the moon, because the rocks from the moon are, they have just brought them down 1967 with the Apollo mission, but there we cannot go there, yeah? It's not possible. So then when we are bringing up our kimberlite, we need a fault. Or we are creating a fault that the kimberlite rises up like a crack in the glacier. So cracks in glaciers, you know what a glacier is, that's ice, yeah? Which is not here in Fiji, one cannot see it here in Fiji, but if you are going to Antarctica or if you are going to the Himalaya or Alps or whatever, where you have glaciers, then you can see that in these glaciers are cracks, yeah? So when these cracks are formed and they are running with railway speed through the ice, so in these cracks you have water, and the water is going with the same speed, yeah? So that's the model what we are thinking. Why the kimberlites are always also running like this, because otherwise you don't get this speed. So when they are running then just here along faults, here we are creating faults, and then they are running through, and here I made a small cloud, and there we have then the kimberlite pipe, which for the is then actually can be found here in Chennai. So, and this is then the way how such an kimberlite looks looks like. Here we have kimberlites, and here within we have an eclogite. So, and these are just from the core shed from the Chaneng mine. I will bring you one of them next week. And they are just there from the core shed. And then you can go there, and I have then sampled different eclogites from these kimberlites. And here is just a 5 Tebe coin. Yeah, that is Tebe are the Pula is the Pula is actually the currency in Botswana, and the Tebe is just a small coin, like like a cent. So, and there we have different pictures. That is the way how it looks like in thin sections. We have there different generations of garnets. These garnets is very well shaped and shows no reaction rims. So, and that is the same garnet inside the kimberlite. Yeah, you have here antiborite is surrounded by antiborite, and antiborite is the serpentine that is formed very late in one of the latest stage or last stage from the kimberlite, while the kimberlite is erupting. And here we have chloride surrounded by chloride, and this chloride is also apart from the kimberlitic melt. So here we have another very nice garnet. So, and here we have a garnet population 1, and here it's surrounded by a lot of small garnets, and these garnets are formed, I have then a very nice picture for you, are formed then by the convective depleted mantle during mantle metasomatism. So here we have an omphacite, you know you have in eclogites always these mineral pairs, omphacite and garnets. So, and here everywhere these garnets and also the omphacite are cross-cutted by small veins, and these small veins, that is all the made by the kimberlitic melt. For example, here we have here a zonation actually of biotite, chloride, antiborite. Here we have a remnant of garnet. Here we have then again amphibole and biotite. And this is all kimberlite. So here another garnet, garnet of generation 1, garnet of generation 2. Garnet of generation 2 is formed due to mantle metasomatism from the convective mantle. I told you this right now. And here I have some other pictures. For example, here we have the garnet is surrounded by huge crystals of calcite. Calcite is then also formed later by the kimberlitic melt. And here a more detailed picture. Here garnet, and here a vein, a zonated vein of amphibole, biotite and antiborite from the kimberlitic melt. And the biotite and the amphibole is formed at higher temperatures, that means in the earlier stage of the kimberlitic melt, whereas the antiborite is formed later at a temperature of about 600 degrees Celsius. Here we have some apatite inside, here huge biotite flakes. That's the way how it looks like, then in thin section. So then they are also chemically totally different. I sampled, there are 5 samples, called this one eclogite 1, type 2, type 3, 4, 5. These are just different samples. So in this, the garnet type 1 has a higher grossular component compared to garnet of type 2. So when that is from here, that is just our mantle metasomatic array. So the high grossular content that shows us that we have high pressures. So, and that was then the original garnet, or these are then just remnants of the original garnet, because you could see in figure 2 that we have at first this thick continental crust, and then this continental crust was removed, or parts of the continental crust has been removed by thermal erosion. Therefore, there is mantle metasomatism. We are heating up our garnet crystals, When we are heating them up, then they are becoming just more rich in pyro, and that is this array. So the same one can see for the biotides, here phlogopite, magnesium rich, here anite, iron rich, and here we have the estonites, siderophilite, and these are then the aluminium rich aluminium component inside our biotides. So then we have here a quad triangle, yeah, that you know this triangle by now, that is used to describe the pyroxenes, and these pyroxenes here, these are omphasites or ethylene orchides. Then we have here some amphiboles, and that is then we are using this diagram, so I'm using this diagram, plotting my mineral inside, and then I know that this amphibole is a pargasite, and these diagrams are used to classify minerals and to observe some trends which can give some information about the Earth's history or the formation of this kimberlite. Like this one. There that is a wonderful trend from here to here. So number 5, yeah, that is now this phase diagram. Let us make it so, let us make it a little bit smaller again. Yes, these are these phase diagrams. And you know from last semester you have calculated Schreinemakers analysis, yeah? So, and from this semester you have, and the last semester you have also calculated these alumosilicate diagrams. So, and here we have such a summary of such a diagram, because in the PD space you have different invariant points, and then I can calculate at which temperature and pressures different minerals are stable during stable at different pressure and temperature conditions. So, and if I are checking this pictures below, you saw this one before, you have the garnet of type 1, then we have garnet here type 2, that is the surrounding area, and here you have the biotides. So, and then I can use these mineral compositions and plot them here into a diagram. Then garnet of type 2, garnet of type 1 was formed here along this ray. So, and then it becomes heated up, that is from here to here. Then we are forming these crystals here, and then we have a very fast uplift to the Earth's surface, and then we have this biotite here. So, and then my PT estimations are finished. So, and for example, then you can, or I use this, you are calculating these diagrams. You can do this all by hand, or you can use computer programs. And I'm using computer program because you have only one time to calculate a few such diagrams by yourself, by hand, that you know or understand what the computer is doing. Here we have the X by rho content in garnet, so that is then just you are using microprobe analysis, calculating the ratio of X by rho. So, and then you know here, this garnet of type 1 has been type 2 has been formed here. So, because I got this pyrope ratio of 0.7 together with a Grossular ratio of 0.12. So, and that you are doing the same way for the omphasites, for the biotides. We must now not go through everything. So, but the resulting thing is now this one. So, and that is our PD path. So, here we have our diamond graphite boundary. Here we have our mental metasomatism. I made here this red star because there we have the uplift, it makes them boom. So, and then we have a supersonic uplift, which is very fast, you know, with a turbojet speed. So, and here we have then finally the emplacement of our kimberlite. And that is a so-called PD path, and that one have to, or can calculate to understand the story behind how our kimberlite, or when our kimberlite has been formed, when our mantle minerals, or at which pressure and temperature conditions our mantle minerals has been formed, and then the calculation of the very fast uplift here. So, and that is now this picture which I showed you at the beginning in the in these micro photographs. Then I showed you these three small pictures below this PD pseudo section, and that is this figure again. Here we have garnet type 1, garnet of type 2, and here we have the biotype, and this green stuff that is just the surrounding kimberlite. So, and the interesting thing is that if you are measuring, or I have measured this from a microscope from here to here. So, and then you get here the XMG inside the garment of type 1, that is from here to here, and that is very constant at 0.65. But if we are then running from here to here, then it increases, and here the blue dots, that is the XMG in the biotypes. So there we have again magnesium. You can see how it increases from here to here. The titanium, it does not increase that much. So, and that is because titanium is an element which is not that mobile. So, but calcium shows the opposite, it decreases. So, and these are very nice trends. So, and this trend shows you our garnet has become heated up. So, because that's always the situation when we are increasing the magnesium, then we are heating something up. So, when calcium decreases, that is always the situation when the pressure goes down. And that is because we have removed, by thermal erosion, parts from our continental crust. So, and based on such measurements, you can then make your models. So then we are stopping here right now, because that is then how I have calculated the fast uplift from the kimberlite to the Earth's surface. And that we can probably not do in 5 minutes. So then we are done for today.